In this video, we're going to introduce Ampere's law, and then we're going to use Ampere's law to find out the magnitude of the magnetic field surrounding a long, straight wire. So in this case, I have a wire coming with current coming straight out of the board. We're going to try to use Ampere's law to derive the magnitude of the magnetic field around this wire. Okay, so Ampere's law is given here. Ampere's law is a fundamental law of nature. That is, I can't derive it from any more fundamental law. It is something that we have observed to properly describe the world, and therefore we trust it. So, Ampere's law, the left-hand side has an integral, and the kind of circle on the integral symbol means that it is an integral around a closed loop. So what that means is that we're going to pick some loop and we're going to take an integral all the way around the loop. That is what the integral with the closed little circle in it means. We take a loop and we integrate around it. What are we integrating? We are integrating the magnetic field dotted with dl. So dl represents an infinitesimal element of this loop. So here I have drawn a few little dl's. They're just little chunks of the loop with a direction that is given by the direction that we are going to integrate around the loop in. So here we're going to integrate around the loop in the counterclockwise direction. So I have all of these little chunks of this loop that I am going to then integrate over to get the entire value that I'm looking for of the integral of b dot dl. Now, to be clear, there is actually nothing at the location of this loop, right? If you have a copper wire coming out of the board, you can just draw an imaginary loop around that wire and then do an integral around that loop. And that is what Ampere's law does. I am not physically putting a loop around the wire. The only physical thing in this picture is the current coming out of the board. And I am mathematically creating this loop that I'm going to integrate around. Why would I do that? Well, because by doing that, I'm able to figure out about how much current is enclosed by my loop. So the left-hand side of Ampere's law tells me about this integral of the magnetic field with my around my loop, and the right-hand side tells me about the current that is enclosed by my loop, which is my current I here. Mu naught is, of course, the magnetic constant. Okay, so in our equation we have dl, we have the magnetic field. Now what we're going to do is we are going to choose our loop very carefully. Specifically, we are going to choose a loop which is a constant distance, which we can call just r, away from the central wire. So I'll draw this in here. So this distance here is r. At this distance, we are going to integrate around the loop, and picking this loop is actually very useful because for our chosen path, the magnetic field, B, is parallel to dl at every point along the loop. And if we remember how dot products work, if two vectors are parallel to one another, then the dot product of those two vectors is simply equal to the product of the magnitude of those two vectors. So because I have chosen my loop very well, the magnetic field is always parallel to my dl around the entire loop. And I used the Biot-Savart equation to figure out the direction of my magnetic field. So we talked about this in a previous video, finding the direction of the magnetic field due to a infinitely long wire. And we learned the equation, or the right-hand rule, that the thumb points in the direction of the current and our right-hand fingers curl in the direction of the magnetic field circulation. So by using that knowledge that we already knew how the magnetic field would look, we were able to choose a path that completely matched our magnetic field in the hopes of getting our dot product of B dot dl to simply turn into a product of the magnitude and dl. Now, this makes our integral a lot simpler. Our integral goes from a integral of B dot dl to an integral of the magnitude of B times dl. And then we take one more step and we assume that the magnetic field has a constant magnitude everywhere on the loop. And this is an assumption that we are making, though it's a good assumption and it's one that we could verify by, for example, doing this problem using Biot-Savart law and taking this integral here. We find that the magnetic field depends, the strength of the magnetic field depends only on the strength of the current and how far away from that current you are. So, making this assumption, we then can take the magnetic field outside of our integral because we can pull constants outside of integrals. So now, instead of having an integral of B times dl, we have B multiplied by an integral of just dl. But this integral is simply the length of my loop. I'm just integrating around the full length of my loop. Well, what's that? It's just 2 pi times r. It is the circumference of my loop. So my integral around the closed loop of B dot dl has suddenly become the magnitude of my magnetic field, the thing that I'm interested in the end, and the multiplied by the length of the loop, 2 pi times r. Setting this equal to mu naught times I get my final equation for the magnitude of the magnetic field due to an infinitely long wire as mu naught I divided by 2 pi